All right, experiment 4 and 5 is here. Very excited about this experiment because it's got something new for you. It's a different form of chromatography that you haven't had a chance to experience. We'll get to that before experiment 5. But in order to run experiment 5, just as we needed in experiment 3, we need a standardized solution. So you're first going to make a standard solution of sodium hydroxide, and then you're going to have to standardize it, you have to do some easy titrations. These are like Chem 1 titrations with phenolphthalein. You're going to, instead of using a volumetric, because sodium hydroxide, when it's in solid form, is super hygroscopic. So when you mass it, it immediately starts sucking up water, and it's really hard to get a good reading and a good, legitimate, accurate mass. So standardization is crucial. Because it's going to be such a weird mass anyway, we're not even going to use a volumetric. We're going to put our sodium hydroxide solid in here, and we're going to fill it to about there. It doesn't matter. You can fill it to here, you can fill it to here, you can fill it to here. It won't matter because we're standardizing it. So you're going to put it in there, shake it, put your little name on the dot. There should be a dot on there like on your other bottles. And you're going to put it at home base. So that is required for the start of experiment 4. Experiment 4 is going to be actually titrating and finding the correct or actual molarity of that sodium hydroxide. You're going to use phenolphthalein. Your sodium hydroxide is in, you can't see that, can you? I can't see it, in your burette. And down here we have a solid acid called KHP. Potassium hydrogen phthalate. KHP is not the formula. So don't sit there when you have to find the molar mass of this, add potassium, hydrogen, and phosphorus. That's not it. It's a really long formula. The formula is on your sheet. You can figure out the molar mass from your lab sheet. You'll need that molar mass because you're going to figure out how many moles you've weighed out. You're going to put phenolphthalein into here. You're going to titrate until it turns pink, and then whatever moles of this you have will be equal. It's a monoprotic acid, so it's a 1-to-1 ratio. It'll be equal to the moles of the base. You'll know how many mils of base, so moles over liters will give you the molarity of the base. That's it in a nutshell. Before and after, you've done this titration before, both in AP and in pre-AP or regular. You did it in regular too, and you're going to run, I don't know why this kid back in the day ran 4 trials. You're only going to run 3. He's hitting in the low 20s, depending upon how many grams of KHP he used. So just super easy. I don't foresee any problems with this experiment at all. It's going to be an easy day. You can probably get all 3 done in a day too, even though you don't have to. Column preparation for experiment 5. So this is really exciting. We are going to run our crystal through a column filled with cation exchange resin. And the point of experiment 5 is to determine both the percent of potassium and the percent of iron in our crystal. So we've already figured out the oxalate. Now all we have left is potassium, iron, and then how much water's on there. So we're getting close to narrowing down our percents to figure out our formula. So we need a column. Let me explain what column chromatography, specifically what's happening in ours. We have our resin. Our resin is innately negative, okay? It's just the little balls are negatively charged. The whole particle is negatively charged. I do something called shocking the column, where before you get this, I'm going to run a very high concentration of nitric acid through the column. And what that does, it's going to saturate all of these little resin balls with H+. So every little black dot you see outside of a ball, those are now H+. And so you can't, this is not a picture that goes with our lab, but imagine this being an H+. So imagine H+ on every single one of these places. So that's what we're doing by shocking the column. That's going to be done for you before you even start the lab. So then what happens, you're going to pour your green crystal when you're running the lab through it. And these are the ions that are in the green crystal that are floating around. So we're going to talk about what happens to each ion. The first is the coolest. This is the whole point of ion exchange. These balls and the surfaces, and you see how everything has these different shapes, kind of indicating a lock and key thing? For all intents and purposes, H plus is a group 1, right? As is K plus. So there's similarities in electron configuration, right? In reactivity. So when we put our crystal into, our liquefied or dissolved green crystal into the column, every K plus is going to swap places with an H plus. So the H plus will release and run through the column. So in our beaker underneath the column, we're going to get H pluses coming out. And those H pluses, every one of those H pluses represents a K plus that got swapped. All right? So that's what happens to the Ks. So we can figure out how many H pluses there are, translating into how many Ks there are, translating into percent of potassium. The next thing is iron. So think about, remember, these things are all covered in positives, right? Positives don't like positives. So when we put our green crystal in, our iron itself immediately is going to go, oh, I hate these positives, get me out of here. And he's going to run down to the bottom of the column and come out. And he's also pretty heavy. He doesn't have the same reactivity or electron configuration or any of the likenesses of those group 1s, so he has no desire to swap. He wants to get the heck away from all those positives on surrounding our little ion balls. Okay? Oxalate. What do you think happens to that? Think for a minute. It's big and it's fat and it's negative. Well, if you haven't thought about it, it gets stuck. Oxalate stays up in the column. It's done. It's like, oh, I love these positives, and I'm fat, and I do not want to travel, so it's going to stick in the column. And then who cares? Water is already kind of a non-entity because we dissolved this in water, so it's going to run through. All right? So that is the chemistry behind this column that we have. Super cool science. I love it. So your column will be in a syringe. You're going to have a burette tip here, and it's called a stopcock, and you're going to control the flow by turning the stopcock on and off. Always, and this is very, very important, keep the liquid level above the resin. Never let liquid drop into the resin. You always want to keep the resin wet. So you're going to, first off, and this is in the instructions, because I've shocked the column, some H pluses may have leached out into the column and left the balls, and you want to make sure all the H pluses that are in there are attached. So you want to check that the liquid coming out is neutral. So you're going to open it up, let some drops come out. If it's acidic, you're going to run water through it with your DI bottle until you get your little neutral indication on your pH paper. Okay? Important step. Because if you don't, you're going to get H pluses then coming out into your beaker that aren't from an exchange of a K. So you're going to get an abnormally high K value. And that's why we want to do that. So experiment 5 itself, you only got one shot, folks, because you only have one column. If you screw up, you're going to have to come back, maybe a lunch or something, and redissolve your crystal, and you're going to have to reshock the column. And I can show you to do that if you come in, but I'm hoping nobody messes up. So you're going to dissolve your crystal in a little bit of water, as little water as you can. You're going to run it through the column, and you're not going to fill it up like that. You're going to do a little bit at a time, and you're going to collect it in a beaker. And then you're going to run a bunch of water through it after to ensure that all the crystal has gone through. Now, if you look, you got very little liquid level there. You're going to beef up the level by adding some water. And you're going to add enough water to, oh, that's all I have on there. You're going to add enough water to actually cover a pH probe. Now, you're going to, let me see if I have that other picture. Yeah, it's just in the wrong spot. So this is what your sensor will look like. You have enough water, and you're going to set it up with the stir so the stir is not bopping into the electrode. Add water to cover the sensor, and start your titration. In the burette is your standardized sodium hydroxide. So why does this titration have 2 equivalence points? This is really cool. Again, love science. The equivalence point here, this first equivalence point, is the OH reacting with our H pluses. So from here to here, volume 1 is the volume you use in your calculation of H plus plus OH minus turning into waters, right? Pretty simple. And again, for every H plus, we have 1 K plus. You'll understand that when you do your calculations. This is the really cool part, this equivalence point from here to here. What's going on here? Well, this represents, and it's actually not the full volume, this is volume 2. The difference between the two volumes is the amount, so we're only going to use this volume amount to determine the amount of iron plus 3. So this represents the precipitation of FeOH3 out of solution. So my question that I always ask is, well, how come the FeOH3 didn't start back here? How come it wasn't until here that we started to see a precipitate form? Because you're actually going to physically see it. And what's so cool about this is why I love chemistry so much, is ferric hydroxide is soluble in acidic solutions. So as long as there's this free H plus floating around, you're not going to see any precipitate. The second all the H plus is gone, bam, that means we can now start to precipitate our ferric hydroxide. So you're going to use this volume to determine the difference, okay? And you'll see, this will make sense when you actually sit down and look at your calculations table. So you're going to start your titration. You're going to start it, it's going to be kind of green, and then all of a sudden, see it's still green, then it's going to start turning red. That's when you know your ferric hydroxide is forming, and you're going to get to see, and this titration you have to do super, super duper slowly because you only have one shot. So you're going to do as many points as you can. You can see on this here, there are 2 equivalence points, so you want a curve that has 2 equivalence points. And it's just super cool. So this is an important day. You need to have a full day. You need to be focused and ready to work. I suggest coming in, running the crystal. If you're busy, run the crystal one day, cover it with parafilm, and then go ahead and do the titration the next day if there's that kind of time. You can do it in one day. A lot of people do it in one day all the time, so you shouldn't have any trouble. So here is our volumes. Volume 1 looks to hit around 11. You have a 1-to-1 ratio with H plus and OH minus, so that makes sense. What you need to watch for is this. For every 1 iron, there are 3 hydroxides, so that's going to affect your calculations. And it looks like the second volume, the second equivalence point is happening at 21.2. So you have all these pieces of information in your table, so your calculations should be pretty straightforward. All right, and this, I think that's it. I don't know why. Experiment 6, we're not doing that yet. That's coming. So you'll see that video next. Have a good one. Bye.